All right, are those machine learning exams breathing down your neck? Don't sweat it. I've got you. We're about to do a super fast cram session covering the entire machine learning pipeline, all the way from messy data to a deployed model. Let's get you ready to ace this thing.
Okay, so here's our game plan, our roadmap for this session. We're going to hit 3 core stages you absolutely have to know. First, generating the data. Then we dive into training and fine-tuning, and we'll finish up with deployment and evaluation. Simple as that.
So let's jump right into part 1, exploring your data. And look, this is probably the most crucial first step in the whole process. Before you even think about writing a single line of model code, you've got to become a data detective. Now, this process has a name. It's called Exploratory Data Analysis, or EDA. And that detective analogy is perfect. Your job here isn't to solve the whole mystery at once. Nope, you're just gathering clues, looking for weird patterns, spotting things that look out of place, and just getting a real feel for what you're working with. It's so fundamental.
So what's in your detective toolkit for EDA? Well, 3 main things. First, you summarize your features. This is just getting the basic stats down, like what's the average age in this dataset? Easy stuff. Next, you have to visualize the data. A picture's worth 1,000 numbers, right? A good scatter plot can show you a trend you would never spot in a spreadsheet. And finally, you start formulating questions based on what you see.
And one of the most powerful tools in that toolkit, the correlation matrix. It sounds complex, but it's not. It's just a grid that shows you how strongly different variables in your data are related to each other. A score of +1 means they move together. -1 means they're opposites. So you might see that, surprise, hours studied has a strong positive correlation with exam scores. That's a massive clue telling you which features are probably going to be important later on.
Okay, so you've explored the data, you know what you're dealing with. Now it's time to actually shape it into something your model can use. This brings us to feature engineering. And honestly, this is the secret sauce. This is what separates a decent model from an amazing one.
I mean, just think about it. Your model can only be as good as the data you feed it. Garbage in, garbage out. So the whole goal here is to transform that raw, kind of messy data into features that are actually meaningful predictors. Getting this part right can seriously, dramatically boost your model's performance. It's a total game changer. So what does this actually involve? Well, here are the heavy hitters you gotta know. There's feature selection, picking the best variables, and ditching the noise. Feature extraction is really cool. That's when you create brand new features from your existing ones. Then you have things like dimensionality reduction and scaling, which makes sure all your numbers are on a similar scale. And finally, categorical encoding, which is just a fancy way of saying we're turning words into numbers so the model can work with them. Okay, our data is prepped. Now for the main event, tuning and training the model. But hold on, before we do, we need to clear up 2 concepts that trip up so many people on exams. We need to talk about parameters versus hyperparameters. And this right here is a classic exam question, so you're going to want to lock this in. What is the real difference between a hyperparameter and a parameter? They sound almost the same, but trust me, they do completely different jobs. Here's the clearest way to think about it. Hyperparameters, those are the settings that you, the human, set before you ever hit train. They're like the knobs and dials on the outside of the machine. You're controlling how the learning process happens. Parameters, on the other hand, are what the model learns by itself during training. These are the internal guts of the model that actually make the predictions. Let's make this even more concrete. A hyperparameter is something like the learning rate or the batch size. You decide that stuff. A parameter? That's the internal weights and biases that the model figures out. And how do you set them? Well, you tune hyperparameters with stuff like grid search, but the parameters, they get adjusted automatically by the training algorithm. Getting this distinction right is absolutely crucial. So, you've trained your model. Now what? How do you actually know if it's any good? I mean, did all that work actually pay off? This is where we get into measuring performance with evaluation metrics. The very first thing to know is that there are 2 big families of metrics. It all depends on what your model is trying to do. If it's predicting a category, like spam or not spam, then you're using classification metrics. If it's predicting a number, like the price of a house, you're using regression metrics. You have to use the right tool for the job. Let's start with the most famous classification metric, accuracy. Super simple, right? It's just the percentage of predictions the model got right. But, and this is a big but, be really careful with accuracy. It can be incredibly misleading, especially if your dataset is imbalanced. Like if 99% of your data belongs to one class.
So that brings us to precision. Precision answers a very specific question. Of all the times the model predicted positive, how many of those times was it actually right? Think about a spam filter. You want high precision there because you really don't want it to accidentally flag an important email as spam.
And then there's its sibling, recall. Recall is all about completeness. It asks, of all the things that were actually positive in the real world, how many did our model manage to find? The classic example here is medical diagnosis. You want incredibly high recall because you just can't afford to miss a single real case of a disease.
So what happens when you care about both? That's where the F1 score comes to the rescue. It's basically a single number that beautifully balances precision and recall together. It's perfect for when you need a model that is both reliable in its positive predictions and thorough at finding all the real positives.
Now, for regression models, where we're predicting numbers, the game's a little different. Here, we're all about measuring the error. How far off were our predictions? Metrics like mean absolute error, or MAE, and root mean squared error, RMSE, tell you the average size of that error. And R-squared gives you a sense of how well your model explains the patterns in the data.
And there you have it. We just crammed the entire ML pipeline. But here's the final thought I want to leave you with for your exam. Just memorizing these metrics isn't enough. The real challenge is knowing which one matters most for the specific problem you're trying to solve. The answer? Well, it always depends on the context. Good luck.